I want to thank CUAHSI and for giving me this opportunity to talk about some of the research we are working on through the Intensively Managed Landscape Critical Zone Observatory. As you can imagine, when I was asked to give the title for this talk, I wanted to make it reasonably broad so I could fit anything, and then I was locked into that title. But I think there is an opportunity for us to understand a part of a landscape which I think is not necessarily well understood. So before I get into the details, I want to acknowledge the work of my students that I'm going to present today, several of them, and in particular also our team with the Intensively Managed Landscapes Observatory, from whom I've had the opportunity to learn a lot. And also I'm affiliated with a WSC Reach project for which Fufula is the lead, and that has also informed quite a bit of what I'm going to present. So this is a picture of the landscape about which I'm going to talk about. This is taken in about this time last year, and it's flat, and at this time it's green. And it doesn't look very complex. And what I would try and do is take off a few layers from that greenery and start looking into some of the complexity that is present in there. What you will notice is this straightened channel that drains this landscape to allow this vegetation to grow. And if you remove this landscape, what you essentially see is a riparian corridor and farmlands and some small townships. What is interesting is that if you look at this at a large scale, this is a satellite picture from NOAA. This is in the denuded landscape is October. The green is August, and you can see the extent of this landscape that is agriculturally dominated and basically stripped off all its greenery. So when we're thinking about the Anthropocene and we want to characterize the changes in this landscape, it is worthwhile casting this concept of change in a historical context. Basically, where did we come from? What is the history of this landscape? So I know many of you are from the Midwest, so you already know this, but what is interesting is that this landscape has been shaped by glacial episodes. And so over periods of time, there were different episodes of glaciers that ran through this particular landscape. And as these glacial episodes happened, they pretty much sculpted the landscape that we see in there. So it's a landscape developed through a process of accretion. And if you drill a hole into the ground, you'll see basically landscape structure that has been shaped through the material that has been brought in by these glacial episodes. So what we see at the top is basically shaped up, at least in Illinois, by the latest glacial episode about 12,000 years ago. But prior to that, about 500,000 years ago, and prior to that, longer time scale. So a lot of groundwater is drawn from Muhammad Aquifer, which is further down deep at around 100 meters level. If we look at the surface, while we see a very flat landscape, if you look at high resolution digital elevation data, what you'll see is signatures of these glacial episodes. So you'll see where the last glacial episode ended. You'll see moraines left over by the glacial signatures. And the drainage basin that exists today is a legacy landscape from these glacial events. And just to give you, make sure I repeat, it was just only about 12,000 years ago that this glacial episode occurred. So from that 12,000 years ago, when the glacial episode ended, it took about 4,000 years for the climate to transition. As you can imagine, a lot of this landscape was iced over and it went through climate transition. And there were vegetation that simply migrated from south up north. And so there is a sequence of succession, establishment of species, and its continued northward migration at about 100 to 300 meters a year was the rate. So it took about 4,000 years before you got to the climax species. If you look at a cross-section of the landscape, you'll see lusts deposited from wind-driven soil and glacial outwash. This template provides the productivity that is for which the U.S. Midwest is known. And if you look at pretty broadly across the U.S. Midwest, this is the extent of the lust deposits. And there are some areas where this may be about 15 meters deep. In other areas, it's about 1 to 5 meters deep. There. So after the establishment of climax species, it was about 8,000 years basically before the system sort of reached a quasi-equilibrium state, if you may. And so there was succession, there was accumulation of phytoorganic carbon, nitrogen, there was a development of heterogeneity, but by and large, then you ended up with a reasonably flat landscape with vegetation that was essentially fire-driven, so it was prairie landscape and a lot of wetlands. And then came the period about 150 years ago with the arrival of European settlement, and as a result what we have done is basically modified the landscape in a period of 150 years. So what you see in the blue lines is the drainage network that existed in about 1820s. And what you see in these light blue lines is what you see presently. So this drainage network has been extended to drain the landscape for the benefit of agriculture. And you see a very sinuous stream, and this is in 1940, and this has been straightened, as you'll see today. So the modification of this landscape has happened at a very rapid pace. And what I want to show also is that this landscape is underlain by tile rings. So these are pipes that pretty much take about a feet and after the landscape and bring water. So you can see the amount of water that is draining is what you see here. It's not just water represented, it's also liquid itself. So, and this you will find at a pretty extent spacing about a few hundred meters under these agricultural landscapes. So what we have here is a straightening of a channel, and these channels are periodically dredged to maintain the conveyance associated with it. And if this dredging stops, these channels tend to go towards a more natural order. And these are basically periodically removed every 5 years approximately. So this landscape essentially is in tension between natural system and human system, and it is maintained so with a lot of anthropogenic energy that is put into this system. So at the end of the day, because of all these modifications, what we have is a system where previously we had long residence time in the system that has been changed. So what we have is a reduced residence time, and the event scale responses are highly accentuated. And so this system has a very fast response to storm events, and the event scale is modified, the dominant processes are altered, and the connectivity across time and space is changed, the threshold effects and cascading effects. And I asked one of my students to basically figure out, in terms of a common currency, say energy, how much energy goes into maintaining the landscape. And she came up with an estimate which is about 5 to 8% of solar energy that is absorbed by vegetation per year. That's the amount of energy that goes into maintaining these landscapes. And a big part of it is the energy that is consumed in the production of fertilizers, which is nitrogen. But there are several other components that go into the maintenance of these landscapes. So it provides a mechanism for us to start thinking about comparisons in a common currency. So we know really that this is a landscape with a lot of human input. So anthropogenic inputs and modifications are directed at overcoming rate limits and rate limiting states of natural systems so as to enhance the productivity from the landscape. That's the goal. Basically, these landscapes were naturally very productive, but for agricultural purposes, we needed more productivity. And so basically, we modified processes that are rate limiting and also states that may be rate limiting, such as soil moisture. And so because of the modification or the selective modification of rate limiting processes, it creates a discord between rate limits of productive processes, which we are interested in, and the rate limits of assimilated processes, which are naturally there. And essentially, this discord creates the sustainability issues that we are grappling with. Because in a natural system, these rates would basically synchronize at various time scales so that the waste is assimilated by the system. But we force the key processes to operate at the human time scales instead of their natural time scales. And as a result, waste has to be transported out of the system somehow. And that is the consequence we see. So the question is that if we want to get to sustainable development, we somehow have to figure out how to manage these rates and associated rate limits and the waste. But that's not the whole story. There are much finer kinds of behaviors that are present in this landscape. And what I'll do is I'll use the landscape template to sort of explain what goes on in these different landscapes. So this will be our horizontal template, and we'll sort of look at the vertical template here. And I'll begin the story with what we are learning about the different constituents, carbon, water, nitrogen, and so forth, and how they are linked. So I'm not going to show you a lot of equations, but my goal is to basically take the kind of information that we are getting from the field and the data analysis and synthesis of prior literature and get to an understanding that hopefully is useful. So the first thing what you can see is that every year there is a plowing of the system or tillage. You may have different types of tillage, but this tillage modifies the surface, and what it does is first of all destroys the near surface macropore structure. And what it also does is basically modifies the carbon profile. So typically, if you don't disturb the land, you will typically have a high carbon content at the surface from the litter layer. But once you have the tillage, this carbon layer is mixed in the top 25 centimeters, the plow layer. And that has its own implications. What we have also done is basically modified the mix of carbon from the natural system, the prairies, to corn, soybean. So it changes the mix of C3 and C4, the constituents of soil organic carbon and soil organic matter. And the tillage and the mix basically have resulted in upland carbon loss due to erosion and the increase in soil organic carbon in the floodplain. So if you try and model this with a landscape evolution model which has carbon movement associated with this, what you start seeing is that if you start with an initial profile, which is typically what you'd expect, sort of an exponential, in the upland area, you get a significant decrease in carbon content near the surface, but in the downslope area, you get a profile which looks like this. So the amount of carbon basically starting to accumulate here, but also there's a middle bunch because of accumulation and the decomposition rate. So at the surface, you start seeing a decrease in elevation level and decrease in carbon level, and at the downslope, you start seeing an increase in elevation as well as carbon. Now, what you can do is you can impose on it that you're mixing this of 25 centimeter every year because of tillage, and that further modifies the carbon profile. So if you include the mixing in here, you have further loss of carbon in the near surface layer, and you get a reasonably complex behavior in there. So this is a modeling result, but it mimics pretty much what we are finding in the field with the data. So going further with this story, you see that because of the tile drain, the water moves through the system much faster, and there is a translocation of carbon due to vertical movement of water. And what this does is this results in a loss of dissolved organic carbon through these tile drains into the river system. And basically, eventually it makes it to the receiving body. If it's a lake behind a dam, then you get a burial of organic carbon and increased production of methane. And so basically, the type of carbon that is now available through our agricultural system eventually makes it to there, resulting in the production of methane. But that's not the end of the story. What you start seeing is its interaction now between carbon and soil. So loss of carbon results in an increase in bulk density, reduced soil cohesion and strength, mechanical breaking of soil, changes in aggregate structure, resulting in increased erosion, increased hydraulic conductivity, reduced water holding capacity, which then further accelerates the movement of water through the system. Further down here, you get post-settlement alluvium deposition in floodplains. These alluvium have higher carbon content because of the erosion, as I talked about before. And because we have created these channels, additional channels, there is, and we have modified the water properties or the variability, there is increased bed and bank area for erosion that is available. And furthermore, because we dredge them, this becomes a periodic sediment source which removes woody vegetation along these channels, modifies the geomorphology, increases the transport capacity, and results in bed and bank erosion. So what you start seeing is basically a confounding of effects. And because we have exposed much of this land through artificial channelization, there is an increased surface available for redox reactions. So you can see some of these things already visually. Okay, so furthermore, you get a modification of macropore flow. There is a modification of freeze-thaw cycle because we have changed the moisture content and the energy balance at the surface, and which modifies the geothermal profile. So what we did was we dug a hole 100 meters deep and put a fiber optic cable through this to basically look at variation of temperature. Normally, if you assume, if you know what the climate model do, the climate models take the near surface temperature and pretty much go some meters depth. So most of the variability is confined to the top several centimeters, and then exponential decline, and then they assume a constant temperature profile. What we are finding is that is not true. The temperature profile has a fairly complex structure, which in some ways is informed by the vertical stratification of the soil that is present. And furthermore, these fluctuations tend to propagate through on a very, very short time scale in there. So although these temperature fluctuations are very small, about point some degrees, they have the potential to affect microbial dynamics and a lot of the biogeochemistry that is further deep in the system. So this sort of starts to get to the complexity of the story between carbon and soil, but then we need to add the water story to it, and some of it you already know what to expect. Basically, this modifies the hydrograph in an interesting way. Because of macropore flow, a lot of the initial water from an event shapes the rising limb of the hydrograph, but once you start get saturated, you get both event and pre-event water mixed in the falling limb of the hydrograph. And this results in a very flashy hydrograph. So you can go out and put some instruments out in the field and see what these tile rains are doing. And here is just one example of a rainfall event and what the tile rains show. Basically, you have a very, very fast response to this rainfall event in spring. And if you go now, the tiles are not draining because a lot of the water is being taken up by the agricultural system. Furthermore, there is a modification of the hypertrophic exchange between surface and groundwater flow. Part of it is basically the anthropogenic modification of these channels, but also loss of sinuosity of these channels. And because we have increased the hill slope and channel connectivity and increased the drainage density, altered the hydraulic geometry structure, which changes the geomorphologic and the kinematic dispersion, it basically changes the way material is transported through the system. So the flasher outflow, increased runoff affects head cut and nick point migration, increases erosion and sediment transport. So now we'll add one more layer, which is basically add nutrients to this complexity. And these tiles sort of act as a short circuit for the nutrient dynamics. So you apply fertilizers, some of it is held into the soil, and what is dissolved makes it very quickly through this tile rain. And that is informed by the structure of carbon that is in the soil and the microbial population, as well as moisture and thermal gradient that exists in there. But that's not the complete story, though. And basically, we don't yet know how long the nitrogen stays in the system at different distances. So one thing which we have been trying to do is, much like we have developed a story for age of water and conservative traces, we try to develop a model to characterize the age of nitrogen or inorganic nitrogen in the soil. So you look at the exchange between organic and inorganic pools of nitrogen, and I won't go through the details. I just wanted to show you that it's a fairly involved model, and then you divide it up into different layers, connect them through, and if you look at, and if you went with a thermal camera and pointed it out to this vegetation, what you'll see is basically this vegetation is warmer. And that is because of higher CO2 in the atmosphere. When the stomates close, they can take in more CO2 and therefore transpire less water because the stomatal conductance goes down. And furthermore, there is a modification of what is called an ACI curve, assimilation and internal carbon concentration, as to how the photosynthesis happens. And the structure of this vegetation will change. Under CO2, the carbon content, the C/N ratio, and so forth are going to have an impact, which then basically loops back to the carbon story. So we went from the carbon, the soil, water, nutrient, ecology, and then brought in climate change, which then loops back to the carbon. So this landscape is changing and has been changing in the last 150 years, and in a way that is very dramatic, in a way that compares with what has happened over the last 12,000 years prior to human settlement. So I think it's a good idea to just take a step back and think about what all this means in there. And what I have argued with you is that there is a fairly deep coupling between water, energy. I didn't talk about energy, but it was implicit in the temperature component, the nutrients, ecology, carbon, and soil story. And it is really, really hard to disentangle one versus the other. There have been a lot of efforts to say, well, a lot of the change in variability in stream flow is caused by tide rain. Yes and no. There are a lot of other things that are also contributing to this story. So we are essentially overlaying the socioeconomic modifications of this, or socioeconomic driven modifications of these very deeply coupled systems, and we are also overlaying the climate story. So this is a system that is changing very fast as far as the time scales of evolution of these systems are concerned. And it is this rate of change that is of significant issue. So one key take-home message is that landscape heterogeneity takes geologic time scale to develop, but we are restructuring the heterogeneity at the decadal to century time scale. So let's think about it. I'm not talking about just change. I'm talking about the complete restructuring of this landscape between upslope and downslope and so forth. So there has been a lot of literature about non-stationarity of rainfall, non-stationarity of climate. What about the non-stationarity of the organizational structure of the landscape heterogeneity and its connectivity? That is evolving under the human influence. And it is evolving in a manner that potentially has significant impact for the climate story as well, for sure, but as well as for water and agriculture and all sorts of ecosystem services. And so the reorganization of the landscape in both character and rate of change has important implications for emergent patterns of transport, pathways, and fluxes, but more important for our predictive modeling efforts. So on the one hand, we have a lot of modeling work that is looking at it from a large scale down, right? So looking at how hydrology informs the climate system or how climate system interacts hydrology, these are at reasonably large scale. What is happening at the landscape is this complete reorganization at much smaller scales, from tens of meters to hundreds of meters. And there is a real need to develop this kind of a predictive capability which can help us to start understanding this system. So we really need to rethink models, because models are informed by available measurements, and a lot of our models were developed in an era where the only measurement, as Ara showed yesterday, was rainfall and runoff. And we have gone past that, and it's time to start thinking about how we can start using high-resolution data that is becoming available into models, and we don't know the answer to that question as yet. So I'm going to just take a little bit of time to talk about some ideas about modeling with high-resolution data within the context of what I have described. Basically, that these landscapes are changing at shorter distances, high resolution, and how do we characterize those into models so that we can effectively look at prediction issues. So this is just a caricature of the kind of information that is becoming available through LIDAR, through hyperspectral imagery. We can map the landscape at very, very high resolution. I'll show you some examples in here. Can we use that to characterize surface textures or the soil properties, and through repeated measurements maybe start looking at changes? Can we characterize the vertical structure of these canopies so we can model light penetration and temperature profiles and start looking at very fine scale dynamics? So this is one example to start showing that if you look at high resolution DEM to LIDAR 1 meter resolution, what you'll see is a distribution of micro-topographic depressions across the landscape. This is an agricultural landscape. And you see some very large depressions. All these dots are very, very small depressions. So we published a paper which shows that basically if you look at the structure of these depressions, it's a fractal, which means a lot of small depressions, but basically a power law behavior. And then these depressions can hold a lot of water, and the residence increase the residence time. And as a result, the biogeochemistry that happens in these depressions is different. So most of our hydrologic models are essentially targeted to fill these depressions. That's the first thing we do, and we drain the landscape. We don't hold water in our hydrologic models in the landscape. And as a result, it's very hard to even start modeling the biogeochemical processes that are associated with these behaviors. The data that is becoming available, as I said, is the LIDAR. You can get point cloud LIDARs with which you can start characterizing the vertical structure of vegetation. Hyperspectral LIDAR, and this is waveform LIDAR, which we were able to collect a couple of years ago. And waveform LIDAR shows a landscape in far more detail than I thought was ever possible. This is a forest canopy, and I'm going to take one tree out of this forest canopy and show you what the waveform LIDAR can show. So this is from a plane, and what you see is the intensity of the return signal. But you can take this intensity and cluster it, assuming that those clusters represent clusters of leaves. And so what you have here is the color of those clusters. And these clusters inform the light penetration through the canopy. Right? If it's a homogeneous canopy, you'll get a different light penetration as compared to where you have very clustered canopy. So this is the kind of information that is becoming available. And we have to figure out how to use them in models. This is another example where we use the hyperspectral data about the same plane and did a classification of trees. So each circle that you see is an individual tree, and then each color is a different species of tree. And the classification accuracy is about 80% in this. And with this information, we can pretty much map the vertical leaf area density of trees. So the integral of this curve is what is the leaf area index. So it's a distribution of how the leaf area index is broken up vertically through the canopy. And this is just an ensemble of several of these different trees. This is characterizing soil texture using hyperspectral data. This was taken for the Mississippi flood in 2011, and this is a mapping of sand, silt, and clay at 7.6 meter resolution. And so you can do this characterization. You can map the soil organic matter and a whole suite of bioavailable nutrients. So will this data become routinely available? And there is a possibility that that can happen. There is a company called Planetary Resources which is thinking of putting a bunch of low orbit satellites which will do the kind of hyperspectral mapping, twice daily revisit rates, weekly monitoring, 10 meter hyperspectral and 15 meter mid-wave infrared resolution. And this kind of data basically opens up a whole window in a way that we can understand our systems. So a big data challenge, I'm not saying the big data challenge, but a big data challenge is how do we maximize the use of information content of high resolution heterogeneous data from these emerging platforms for improving predictive capability. The key is not to answer the same questions that we have been trying to do for whatever period of time, but address new scientific questions, and that will definitely require basically some different way of the way we compute. and just because of the size of this data and the number of variables in there. And it brings to the fore a whole suite of issues, basically, that when these data become that dense, can you extract useful information out of this, and how do you use them, and so forth. So one effort that we have been doing in our group and as part of our CTO effort is basically take some of the models that we have been developing over the last several years and extend it into three-dimensional in a way so that we can look at vegetation process in high resolution vertically. We can look at surface transport, but with the full recognition that there are micro-topographic variability associated on the surface, as well as subsurface flow, and all in 3D. So that requires basically dividing this up into layers and grids, and solving a suite of equations as we go along and integrating them. So I'm not going to bore you with the details of this, but that's the kind of framework that we're starting to think about, and with the goal that basically we will be able to then develop an understanding of the interaction between surface and subsurface process and deep surface and vegetation processes. And it's not just the water and the nutrient story, but we can add transport, sediment transport, we can add carbon cycle components in there, and perhaps weathering and so forth, to basically start to look at how this landscape not only just produces fluxes, but how is it reorganizing. And you can potentially use some of these LIDAR data to define the vertical canopy profiles. So ingest these data directly into these models. And in terms of the computational story, I mean, it is a real challenge. So what we are doing in our group is looking into hybrid computing between MPI architecture and GPU architecture, and developing the communication so you can actually do this high-end computation. I'm going to show you results from one of these simulations in there. So in one of our basins, we have a mosaic of agricultural fields, and we wanted to understand how will the soil moisture be different under climate change scenario versus present scenario. So you can see basically the simulation. This is the elevation, and it's hard to see the variation of moisture because of the density of this grid. But if you take a cross section just along a channel, you can see basically that near the channel you have deeper penetration of moisture, and away from the channel you have less penetration of moisture. And you can start asking questions as to which areas of this landscape are going to become drier under climate change and otherwise. And you can see where the topographic depressions, the moisture conditions may be different presently or in future climate. So this is a difference plot between a future climate with a higher CO2 and no temperature differential, and a higher CO2 and a temperature increase. So the moment you can crank up the temperature, the soil goes dry, and the way this moisture is distributed across the landscape is very different. So we are trying to crank this up to go to larger and larger scales, and so we're running a simulation which is 40 by 60 kilometers square, and you immediately get into tens to hundreds of billions of unknowns in there. And so you have to use whatever tricks are available up your sleeve in terms of computing technologies to actually solve this issue. And you can see some interesting patterns. So if you put uniform rainfall on a landscape, just the topographic variation structures this moisture variability in there. So you have a stream channel here, you have roadside ditches, you have micro-topographic variability, you have potentially have signatures of tide rains in here. And so when you scale up to the satellite scale, satellite is going to see an aggregate of this. And so this might be a way to basically bridge the gap between what you're seeing at the satellite scale versus a smaller scale. Now, on this, we can add the nutrient dynamics associated with carbon and nitrogen dynamics and start to examine whether this topographic variability has an impact at all on the nutrient and the carbon dynamics. And the answer is yes. We look at basically a small simulation of about 200-meter grid. And if you look at the vertical profile of carbon in the upland versus the downslope area, you see some differences. The upland area, the kind of erosion, it just does not have erosion, but it's still a lower amount of carbon simply because of the decomposition. So higher moisture content in this region suppresses the decomposition of carbon here. So adding the erosion landscape evolution on top of it will further give us more information. Now you can also take this and start asking the age story. Is the age of nitrogen across these landscapes different? So you can basically see that the nitrate age versus ammonium age is structured in some ways according to the topographic variability, as well as basically this is being a dissolved compound versus this which adheres to the soil a little bit more. So without going into the details, the key here is that it appears that the hypothesis that micro-topographic variability across the landscape will have an important bearing on the nitrogen and the carbon dynamics, on the water dynamics, and erosional processes and so forth will bear out. And so that begs the question, should you come at it from top down or should you go at it from bottom up? And it's a question of scale. What are the things that you're trying to resolve? So if you were to go from bottom up, what is the understanding that we develop? So we have to understand the processes that operate at the plot scale. So there are a whole suite of processes that operate at the plot scale, but the moment you scale it up, it is not just a question of putting in a larger grid. It's a question of adding up more processes. So at the hill slope scale, you have what is happening at the plot scale, but you have new suite of processes that emerge as the scale changes. And so the computational systems have to really start incorporating that. And then the moment you go to a small basis scale, you have everything here plus additional processes that kick in at the small basis scale. And so you can take it up a notch further and you go to a large basin. It's an integral of this plus human infrastructures and so forth. Right? So when we are scaling up, we really need to think about what is it that we are trying to scale up and how these dominant processes change, how do these interact, how do large-scale processes affect small-scale processes, and the other way around. And so this is a cascade of systems, and because of the decoupling and the heterogeneous reorganization of this landscape that is going on, we really need to think hard about what our models really do. I'm going to skip this. So with that, I mean, I'll list three key ideas that I'll try to present today. One is that the significant anthropogenic inputs in intensively managed landscapes are to overcome rate limits and rate limiting states for enhancing agricultural productivity. And the second is this landscape is being resculpted. Heterogeneity and connectivity are not stationary, and they are operating at decadal timescales rather than the geologic timescales which you believe. So a lot of the heterogeneity that we represent in our models, which we assume parameterized and constant, they may no longer be. And the third is basically to explore opportunities for new ways to do modeling and in this data-rich world. And basically, we can't be basically saying that well, a lot of these models we have, how do we modify them? Because those modifications may just not be appropriate. Maybe it's time to rethink from first principles as to what is the new world that we're looking into and how do we model that. And we have to characterize predictions in two forms. One is trying to predict what is going to happen in the future in terms of specific clusters, but also are there new phenomena that we may be able to discover because of this modeling? Maybe the way the carbon profile changes or the nutrient profile changes. So we are not doing enough in hydrology with this phenomenological prediction associated with modeling, and we seem to be too constrained with calibration and equifinality and all that other stuff. We basically stunts our thinking. So one thing about the future is it comes to us a little too fast and it becomes present very quickly. I'll leave you with that thought. Thank you very much.
So Praveen, in the scaling up, what struck me is you typically think about going from, coastal up to large basins. You're always thinking of the basin as a unit. So we're back to what Dara said yesterday about maybe watersheds not being the correct control volume and thinking beyond that. And in context of what's going on with the National Water Model, how do you think we're going to scale up when we're actually talking about predicting a series of reaches like in the NHD plus, and really thinking about the accumulation of water through the landscape? So it isn't that the entire basin is one big unit, but rather we're dealing with incremental reaches and figuring out what the changes are going to be along those regions.
Yeah, I mean, so if you're just thinking about reaches, I mean, you have to figure out how much water is coming into that reach in the first place, right? So that is your bottom line, and whether there are backwater effects that need to be considered and so forth. So, I mean, in the present water model with the routing scheme that is there, I don't think that is being accounted for in other ways. I don't know the details of what's being in there. But also, the national water model is focused on flow in the reaches. And what I'm talking about is basically accounting for everything in the, so the connectivity between the reach and the landscape and so forth, and the structure of the valley and all that is going to play into the role.
Thank you. I'm Shayu from the University of Delaware, and I want to know when we have the micro-topographic model in the road and flow processes, how detailed of the temporal dynamics of this micro-topography to determine we should think about.
What say that again? How detailed what?
How detailed of the temporal resolution and of the micro-topography we want to think about when we consider watershed hydrology.
So the thing is, I mean, the micro-topographic variability is static at the time scale that you're considering, but we need a high resolution rainfall data essentially to characterize that, and that is becoming available more and more in there, not at the type scale at which you're talking about, but even with a uniform rainfall, you see very different heterogeneity across the landscape, just basically structured by the topographic features. So we don't have an even understanding of that as yet, as to even as a uniform rainfall what it is. So a more heterogeneous rainfall is going to give a very different picture in there.
Hi, my name is Chris. I'm from Duke University, and I was wondering, since we use tile drains all over for draining fields for corn and such, and our economy thrives on having cheap corn, do you think there's some opportunity for you to inform farmers how to use tile drains in a more intelligent way, perhaps more restricted, more accurate way, so that their impact on hydrologic cycles?
Yes, I mean that is the goal, essentially that you understand how the system behaves and you inform the farmers. Having worked with them, I mean I think there is a pathway that you have to take to actually get to there because the farmers deal with trusted parties. So going through extension programs and informing them about these things is a much better avenue than just going and talking directly in there. So there are institutional mechanisms in place to inform that practice in there. But definitely that is the goal, to be able to do that and inform what's going on there.
Hello, I'm Vinod from the University of Alabama. I would like to know whether the CERES database for hyperspectral imagery is readily available, or how do we access it?
No, those satellites are not deployed as yet. I was contacted by the folks from the Earth Resources. They are thinking of deploying it in the next year or two, I believe. And what they were trying to do was do some flights during this summer to test some of those instruments before they are deployed in there.
Hi, I'm Linda Lilienfeld. I would like to talk about water, and there'll be a film tonight at 7:30, which Rick mentioned. But Praveen, I have to tell you, this was such a beautiful presentation on so many levels. And we worked together in Champaign with the film, but you have philosophical layers as well as informational levels, as well as visual. And it seems to me, having been with CUAHSI for about 12 years, that this is a watershed moment for the field of hydrology because of the visualization that technology can make available, and because of the scaling up, having to deal with going from plot scale to large. And it's very interesting. Last night, the gentleman said that we think globally, so now we don't have to think in a watershed scale. And it seems that every time I come to these conferences, there's always something that takes what is existing and throws it out a little bit, and then how are people to work together to make the public understand things more clearly? So what the question I have for you is, the imagery is so vivid and clear, and when you think of how many people need to understand what you are doing and talking about, and people access information in socially mobile imagery, are you able to make small videos in your department to be able to inform people and sort of promote them to a wider public? That's one question. The second one is, following the National Water Center discussion with Tom, the idea of the role of soil in understanding water flows and the role of the USDA in the National Water Center in terms of linking how soil affects water flow and flood prediction and flash flood prediction. Two different questions.
Yeah, no, we have done some videos as part of the CZO project, and I can show them to you and see, and certainly we can do more with them. But I mean, I agree with you. I mean, the role of soil, but I think it's just not soil, as I was trying to say. I mean, it's the evolution of the characteristics of the soil with the carbon and the hydraulic properties that affect it over a time scale of decades. And I think there is a need to evolve towards that modeling. I'm pretty sure we're not there yet, but I think we need to come at it from both spectrums. And one is the global spectrum, which Dara presented very eloquently yesterday in terms of understanding the role of soil moisture in the whole story. And then, but we don't want these kind of reorganization of landscape as a structural reorganization to get lost in that story, assuming that, well, this is not changing and it's not important. Because if we are to implement solutions, they are not going to be a large-scale solution. They are going to be at smaller scales, because that's where the problem was created in the first place. A lot of small-scale effects. And so I think we need to go back and figure out if there is a different way of precision management of these landscapes and how that solution can be implemented. But we need to have very precise information.
Hi, Josh Lieberman, Harvard University. It's really interesting connecting these small-scale, particularly agricultural field processes, to the larger cycles, and kind of alarming because both the intensity of modern agriculture and the ability to change the landscape is kind of accelerating. For example, you know, there is spreading practice of controlling soil moisture by having very dense canal networks together with mechanical irrigation. and added to different tilling techniques. Are these observations ready to apply to some of these practices before they become widespread without that sort of input?
I don't know the answer to that question, because a lot of what we are understanding is not that small a scale, but it's still a smaller scale than what it would be broadly applicable. But I think a lot of the principles that we are getting out of this is potentially scalable to larger scale, but that will require some translational work there.
Okay, I'm Jim Butler with the Kansas Geological Survey. I have a question about stationarity. And one issue you didn't address explicitly was that of agricultural practices. And I would think we can consider those, again, non-stationary because of the revolution in agriculture with precision agriculture coming to the fore. I was wondering if you could just talk about the ramifications of that revolution in agriculture on this landscape resculpting.
Yeah, no, I definitely agree. I mean, agricultural practices has gone through a lot of change, going from intensification to conservation agriculture now. And there are some examples where you can actually show that the soil organic carbon had declined up until the 1990s and starting to recover because of the conservation agriculture practices. So that was not the point. I mean, I agree with you that these agricultural practices have gone to change, but what I wanted to point out is the cascade from one element to another to another to another. The interlinking is what is is an important aspect. So if you do better in one, it will have some cascading impact across the other. The question is there a way to optimize across the carbon story, or do you want to optimize across this interlinked story? I mean, those are the kind of questions we could begin to ask. Thank you very much.